Now we discuss the scaling formula for surface integral. So suppose S is a smooth surface. We define the Rs to be Rx x in S. Okay, and F is continuous. F is continuous from Rs to R. Continuous. Then the result is that the integral of F over the surface equal Rn minus 1 integral of S f r y d sigma. Maybe I should write this as ry. That is x equal ry. So this is a surface S. No. So another surface Rs. So y is here. X equal ry is another surface. 0 is here. Okay. The proof is very easy. Just by the definition of the surface integral. Proof. This is the idea is the same of the case when n equal to 3, which is a quiz question in the question 4 in last quiz. Okay, so we take a parametrization. Suppose the parametrization of S is y u to Rn. That is a map y here u in Rn minus 1. This is the parametrization of S. Then the parametrization will give a normal vector. The corresponding normal vector n is y2 yn u1 un minus 1 minus 1 n plus 1 y1 yn minus 1 u1 un minus 1. Okay, we know how to compute normal vector once a parametrization of a surface is given. Then we know that this map from u to x equal to ry is a parametrization of Rs. X equal to ry, that is a map from u to Rn, is parametrization of Rs. This is obviously true. And the normal vector n tilde, so this is n tilde. N tilde is given by x2 xn u1 un minus 1 minus 1 n plus 1 x1 xn minus 1 u1 un minus 1. But because by the relation of x and y, we know that dxi duj is r dyi duj. Okay, so every component of n and n tilde. For example, we consider the last component. These components are n minus 1 ordered determinant, but every entries in this determinant is the multiplication of r, which the entries corresponding entries of the component of this determinant. So we know that n tilde is Rn minus 1. This is important. Equal Rn minus 1 n. At the same u, n tilde at the point u is the Rn minus 1 nu. N evaluated at the point u. Okay? The same u here, given the u here, the corresponding n is here, the corresponding n tilde is here, then n tilde is Rn minus 1 nu. This is the relation between these two normal vectors. Why we have the vector Rn minus 1? Because the entries in this determinant are Rn minus 1. R times of the entries of that determinant. Maybe I should write this out. This, for example, we consider the last component. That is determinant dx1, du1, dxn minus 1. Maybe no. dx1, du n minus 1, dxn minus 1, du1, dxn minus 1, dun minus 1. This is the determinant here. Okay? Now, this entry are R times of that of y. So we write this is just R dy1 du1, R dy1 dun minus 1, R dyn minus 1 du1, R dyn minus 1 dun minus 1. Okay? So this is n minus 1 by n minus 1 determinant. Therefore, we have Rn minus 1. Move the Rn minus 1 out. This is the last component of n tilde. And the right hand side is Rn minus 1 multiplying a last component of n. So from this, we know that the n tilde and the relation of n tilde and n is that n tilde at the value u is Rn minus 1, n at the evaluated at u, when u equal to u. Okay? So this is the relation. Which this relation, the result is easy. So we get Rs fx d sigma. By definition, this surface integral we use the parametrization of Rs. Parametrization of Rs, that is our map x here. So so we should write this is u f xu. Xu is ryu. Then the norm of n tilde u du. So this is u f r y u. The norm of n tilde u is Rn minus 1, the norm of u. Then the Rn minus 1 move out of the integral, we obtain the Rn minus 1 u f r y u nu du. But this is just the integral of f r y over the surface S. That's proving our scaling formula for surface integral. Okay.